Hi everyone, here we are going to see about applications of mathematics in diffusion of liquids. Here we are going to see the introduction of applications of mathematics in diffusion of liquids. Transfer of heat by conduction is also due to random molecular motions, and there is no analogy between two processes. This was recognized by Fick in 1855, who was the first person to put diffusion on a quantitative basis by adopting the mathematical equation of heat conduction derived some years earlier by Fourier in 1822. The mathematical theory of diffusion in isotropic substances is therefore based on the hypothesis that the rate of transfer of diffusing substance through unit area of a section is proportional to the concentration gradient measured normal to the section. As you can see here, F is the rate of transfer unit area of section, C is the concentration of diffusing substance, X is the space coordinate measured from normal to the section, and D is called the diffusion coefficient. In some cases, example, diffusion in dilute solution, D can reasonably be taken as a constant, while in other examples we can say as diffusion in high polymers. It depends very markedly on concentration. Here in this slide we can see differential equation of diffusion. The fundamental differential equation of diffusion in an isotropic medium is derived from equation 1.1 as follows. Consider an element of volume in form of a rectangular parallelepiped whose sides are parallel to axis of coordinates and area of length 2 dx, 2 dy, 2 dt. Let the center of element be P of xyz, where the concentration of diffusing substances is C. Let A, B, C, D be the faces of perpendicular to the axis of x. Then the rate at which diffusing substances enters the element through the face ABCD in the plane x dx is given by 4 dy dz of fx minus dou fx dx by dou x. Here in this slide, where Fx is the rate of transfer through unit area of the corresponding plane through P. Similarly, the rate of loss of diffusing substances through the face ABCD is given by 4 dy dz of Fx plus dou Fx by dou x of dx, as we can see in the figure clearly. Here in this slide we can see diffusion in a cylinder and sphere. Other forms of the equation followed by transformation of coordinates or by considering the elements of volume of different types. By putting x equals to r cos theta, or by considering an element of volume of a cylinder of size dx r d theta dz, y equals to r sin theta. We obtain the equation for diffusion in a cylinder as follows, as given below. You can see. Here we can see conversion of heat flow to diffusion solution. The equation diffusion theory is based on fixed two equations, where C is the concentration of different expressed in mass per unit volume and D is the diffusion coefficient. The two corresponding equations in heat flows are where 0 is temperature, K is heat conductivity, P is density, and C is specific heat. The space coordinate is x and time is t. F is the amount of heat flowing in direction of x increasing per unit time through unit area of a section which is normal to the direction of x, as follows, as you can see down there. Here in this slide we can see boundary conditions as first one, prescribed surface temperature corresponds to prescribed concentration just within the surface of a plane sheet. If the surface of a contact with the vapor at pressure P, there is some relation between P and C, such as C equals to Sp, and where 5 is the solubility, there is no analog to S in heat flow. And the second one is prescribed heat flux corresponds to flux to diffusant, and we have minus k dou T by dou x equals to f of T in heat, and minus d dou C by dou x equals to f of T in diffusion, where f is the general as known as function of a time, may be constant. C, a heat insulated surface, corresponds to an impermeable surface and is a special case of f equals to 0. Dou C by dou x equals to dou 9 by dou x equals. Here in this slide we can see the conclusion. The diffusion equation must be similarly modified if the diffusing substance is created or removed as diffusing proceeds. We identify A as the rate of creation per unit volume and Cp equals to 1 and K equals to D. Problems in heat flow may involve moving boundaries on which phase changes occur, accompanied by the absorption or liberation of latent heat. The velocity of the transformation boundary at x of t is related to the difference between the rate of heat arriving and leaving it by conduction by a condition of minus k1 dou t1 by dou x plus k2 dou t2 by dou x equals to Lp dx by dt. Thank you.